Hello and welcome to RF Design Tutorials. This is a three-part video series in which we will demystify SMA to RF board assembly and analysis. This is part 1 video of the series, and in this video we will talk about importing your vendor 3D connector models or modeling your own 3D SMA connectors, and then we will take a look at how to use those 3D models in your ADS design, and I will show you various examples for edge mount and top mount SMA connector with your board. Now this video will set up a complete foundation and clear all the fundamental issues while dealing with such geometries. Beyond this video, in part 2, we will talk about optimizing and designing the SMA to microstrip and strip line transitions, and finally in part 3 videos we'll put it all together to understand how SMA and enclosure effect can degrade your RF circuit performance and how to avoid such distortions in your RF circuit. Alright, so hopefully you are as excited as I am. So let's go ahead and talk about all the topics we have lined up for this video. Now let's start with importing vendor 3D connector models. Now as you understand, to import any 3D connector model, you first need to find a vendor who's giving you the 3D CAD file, which then can be imported in any of the CAD tool you are using. For this demonstration, I'm going to use Keysight EM Pro, which is a standalone 3D CAD environment, which allows you to do standalone 3D simulations if you need. But here I'm going to use EM Pro as our 3D CAD editor and a gateway to Keysight ADS tool where our circuit design work is happening. Now in reality, you shouldn't be seeing EM Pro and ADS as two independent things, because once you install ADS, if you don't know that, it might be a surprise, but once you install ADS and if you follow the installation path where you have installed a specific release of ADS and look inside the FEM folder and follow this path based on the version which you may have, inside the bin directory you can see you already install EM Pro when you install ADS. However, you can also have a separate installation of EM Pro by downloading it from the website. So either of these two should be good enough to work for our application. And the EM Pro license nowadays is tied with your ADS license. So essentially you do not need a separate license to run EM Pro as long as you have the latest copy of ADS in your place. So here, as you can see, you have a full-blown EM Pro 3D CAD editor which is available inside ADS, and now you can start using it for any of the application which you may be looking for. Alright, so once we have the EM Pro opened up, we first need to find a vendor who gives us the 3D CAD model. Now for this demonstration, I'm going to use signalmicrowave.com, and the beauty about this website is, or this vendor is, they give you all the 3D CAD models in an open format. So it's not tied to a specific tool, such as some of the vendors provide encrypted models which is encrypted in a specific tool. Then you always need to have a copy of that tool and you really can't see the 3D geometry of the connectors to understand it better. But either way, this is the website I'm going to use. And here, if you look under products, you have variety of connectors, and for our demonstration and discussion, I'm going to use an edge mount or L40, which is a 2.92 mm connector, goes up to 40 gigahertz. By clicking on that, you get access to its data sheet and some reference board assembly details or test board data sheet. And here, as you can see, you have variety of files which you can download. What I'm interested is downloading this 3D data for L40001 connector. By clicking, it simply downloads a zip file. Let's go ahead and open the zip file here. And here, let's go ahead and archive that file. So after archiving, what you will notice, you have access to both the mechanical 3D CAD model as well as the 3D simulation model, which is what RF microwave engineer really needs. And also it has an outline. So I'll come back to this PDF. Now first go ahead and take a look add all the files it is providing. So you have IGES file, SAT file, STP. So that's good enough to be used for our application. Now in RF Pro or EM Pro rather for now, so we go to File, Import, and you can see you can import variety of formats. So even if your vendor is giving you HFSS file, or if you already have your HFSS design, you can also import those files into EM Pro and then use it inside ADS. So for now, let's go ahead and use a CAD. And now we can browse to the folder where we have downloaded our model. And under simulation model, I'm going to import the SAT file. Click open, and now it detects everything. Click OK, and now you have the 3D CAD model imported. You can see the geometry. Under parts, you can see all the three main parts of this SMA in terms of center conductor, the dielectric core, and the housing. But right now, as you can see in the tree, there is no material because SAT file is only the 3D CAD model. It does not have any idea about the material. So how do we find material details? So let's go back to the same folder here. Remember, we have an outline PDF file. Now, if you open that PDF file, you can see all the relevant details about, that connector, including all the dimensions and everything, just in case you would like to double check whether your imported model was accurate or not. Now here in the sheet, you can also see the housing material, which is steel, stainless steel. You have dielectric, which is neoflon, and the center conductor is beryllium copper alloy with the gold plating. So you have all the enough information. Now, once you know the electric characteristics of these material, you can go ahead and add it here. So let me show you how quickly you can do that. In materials, if you right click, you can either add a new material definition, or you can select the material from the library. So here, by going to the library, of course, we have a gold. So we press G and look for gold. And here we have the gold material. So let's add it. And also the second material I'm going to add is a PTFE, because neoflon is a format of the PTFE with a slight different, kind of dielectric constant. So here, let's go ahead and click P. And now in PTFE, you can see there is a default material which is available there. So we'll go ahead and add that. Now for stainless steel, if we have to create our own material, just to show you variety, I can simply click, add a new material definition, and let's call it steel to keep it simple. And now double clicking on it, I can define the conductivity or the permittivity depending upon what you're adding. So it's a steel, it's a metal. So let's enter the conductivity as 1.4 E6. And also under appearance, I can choose the color which I would like to assign to our material. And let's keep it something like this color. Click apply, done. So now once I have all the materials listed, we can now assign it. But before we do the assignment, remember PTFE. Now this PTFE has the permittivity of 2.06 and the neoflon is around 2.5 or 2.6. So I'll go ahead and enter 2.6, which is good enough for the moment. Now I have all the three materials. How do I do assignment? Well, take gold, drag and drop it to the object where you want to assign, and you can see the color change in the geometry. Similarly for PTFE, let's drag and drop it to dielectric, and finally the steel to housing. So now we have assigned all the three materials to three objects we have in our design. Now notice here is a very simple model. So whenever you think about dealing with SMA connectors, there's no need to make it very complicated. It is at the simplest level. It's just a coax, kind of cable connector, right? So you have a center conductor, you have a dielectric core, and then you have a metallic core. Now, as long as you can model those, it's good enough. And most important thing here is actually the center pin, which is going to land on your board or which is going to connect to your board, because that is where you may have the impedance transformation or impedance mismatch when you are launching the energy from the coax to your board design. Because remember, on this side, you have a nice coax, which is a full kind of proper propagation. But once the energy gets launched from this pin to your board, and that is where you need to make sure the transitions happens as smoothly as possible. So even if you don't have this vendor 3D CAD model, I will next tell you how can you model your own and which is the easiest way. So don't make it too complicated. SMA connector, just a simple coax transition. Now different vendors may have different IP involved to extend the frequency range to 70, 100 and so on gigahertz. In those cases, of course, you can go and obtain much higher accurate model. But if you just want to do a simplistic modeling, just go ahead with a simple coax transition. That sets the fundamental and the foundation for your circuit design. All right, so once we have the model, we have all the material assigned. Now how do we use this model into ADS, a circuit domain? Well, we can save it into a library, and then we can use that library in ADS. And one EMPRO library can contain hundreds of parts, and all those parts will be available in ADS once you add that library. So let's see how to go about it. So here I'm going to save this project. Before I do that, I would also like to assign a coax feed here or waveguide port. It will serve two purposes. One, we can apply the waveguide port and then simulate the port to make sure it indeed is a 50 ohm port as we are hoping. And then this port can be accessed in ADS to provide the termination with the rest of the circuit design or assembly design what you're doing. Now, how do we assign waveguide port in EMPRO? It's pretty simple. You see the circuit component port category, right click, and now you can define various kind of ports here. So let me go ahead and define a waveguide port. Now, as you might understand, in waveguide port it has to be applied to a phase. So let's click on this arrow, select the phase where we would like to apply, and once the phase is selected, you can go ahead and define rest of the properties. So here I selected this phase, go to boundary extension and limit the boundary to the face of this connector. In properties, I'm going to use 50 ohm voltage source, and an impedance line, which is basically your impedance calibration line. Let's go ahead and select the plus by clicking on this arrow, or you can enter your own XYZ formula. But here I'm going to select the center point of the conductor. You can see the XYZ filled up, and by clicking on next arrow, I'm going to click on any point on this face or the body, which is basically the ground. Once done, you click apply and you can click done, and now you have a waveguide port. Now another interesting thing you notice is this connector is offsetted from the origin a little bit, and this is not a problem, but this is something it will be nice to remember. And if you orient your design in a proper 2D view, you can see the origin is right at the center of the the z-axis is aligning right at the center of the center pin. Now why all these things important, you will come to know once we start using this model in ADS. But whenever you import any model, just make sure you understand where is the origin point, especially the Z origin, because this is what will be used when you try to align it with the rest of circuit design. So it's very simple, but something you need to be mindful of. All right, so once we have the port, we have the connector, we are going to save this model. Now here, for simplicity, I'm going to create a library on my desktop. And to create a library, you can either create a new folder, it will become library, or explicitly click on this icon, which is create a new open access library. Now here, let me name this library as demo_video lib. Now inside this library, I'm going to save this part, and I will just keep it the same nomenclature as the vendor. So here I would say ELF 40 SMA, right. So this is an open access project which I'm saving. Now the data has been saved. Now how do we ensure that the port I applied is a 50 ohm or this coax interface is 50 ohm? Well, double click on that port and simply simulate it. Now this is basically not simulating your entire assembly. It is simply simulating the port which you have applied and now you will be knowing whether the imported dimensions were okay, the coax phase is giving you 50 ohm and so on. So it's a pretty quick analysis, and after simulation we can look at the results in the window, look at impedance ZPI as we call it, based on power and current. And now here in the resulting table, you can see for all the way up to 10 gigahertz, the impedance offered is around 49.2 ohm, which is pretty good. So it's a nice 50 ohm connector. So in no time we have created our model. Now if you have more models which you would like to include, you can keep following the same method by importing more and more connector or inductor capacitors or whatever models you have. Keep saving it in the same demo video library, for example, and now that library will be available inside ADS. Now before we go and use this library in ADS, let us also talk about, in case you do not have a 3D CAD model, then how can you model your own SMA connectors? It's a pretty simple modeling, but let me show you how you can do it in EM Pro very easily. Alright, to do so, let's minimize this and let's create a new project. Let's start with an empty project here. Alright, so once we have the empty project, now think about SMA connector as we discussed is a simple coax, and if you consider any SMA, for example, if you go to a website and just do a SMA flange connector, for example, you can see there are a wide variety of connectors you have. Most probably you are either using this kind of SMA or you are using this kind of SMA, which is like a flange mount, right? And here if you notice, you have a center conductor which is like a cylinder, then you have a dielectric cylinder, and then you have an outer metal shell. So these are basically three concentric cylinders of different diameters or radius, and then you have a mounting flange on top of it, right? Pretty simple. So now let's go ahead and model simple three concentric cylinders in EM Pro. And to do so, you have a variety of ways. You can go to create geometry, you have 2D to 3D transformations, or you have these 3D primitives, so you can use, and same thing available on the toolbar. So here, let me go ahead and just pick a cylinder. And here you can enter the attributes of the cylinder. But before that, for ease of use, as you remember, ADS or any circuit design environment is usually utilizing X and Y plane. So basically anything which you are drawing should be in XY plane. But here you can see the connector is basically orienting, or the cylinder is orienting in Z direction. It's not a problem because later you can rotate it once you place in ADS, but why to do so? Let's go ahead and start from the very beginning. So that means basically our drawing plane will be YZ, and I would be doing all the operations in X direction. So for that, let's go to specify orientation, simply select the right axis, which is YZ. And now you can see the origin point is right at the center of the cylinder, as you would expect, and now you can enter the cylinder attribute. Now how do we know what should be the radius or diameter of center conductor, outer conductor? You can either work through your theory formula, or you can use website something like this. I like this website because it has a lot of calculators built in. So in Pasternak, here I can enter my dielectric constant. Let's enter PTFE, which is 2.06, and let's change the units to millimeter for ease of understanding. And here I know a couple of formulas which are numbers which will work. For example, inner conductor diameter of 0.2 mm, outer conductor diameter 0.66. So calculate, and now you can see it's a nice 50 ohm kind of coax, right? So I'm going to model this in EM Pro. So let's come back. Let's enter the base radius. Let's enter 0.2, which gives you diameter of 0.2 as we just calculated in our Pasternak calculator. And here you can see now you have a conductor of that radius, and the length or the height we can keep it something like 4 mm. And again, it's up to you. It doesn't matter how much long you keep it. And let's call this as inner pin. So you can keep naming the objects as you're creating it. So when you say done, you can see you have an inner pin object here. So now I can either draw 3 more cylinders like what I did, or I can simply right click, edit, copy, and now I'm going to paste that in parts here, and we are going to paste it once more. So now I have 3 objects there, and let's start renaming it first so that there's no confusion. So I'll say core, and let's say this is outer. Right. So once we have 3 cylinders, simply open the modeling sequence, double click, and here let's change it to 0.33, which is basically 0.66 diameter. As you can see, the object changes, its core. Click OK. So now I have 2 concentric cylinder. And finally the outer one, and outer is just a metallic shell, so really it doesn't matter how much radius you keep. So I'm going to go ahead and keep it like 1 mm, which is like this. All right, now one thing you notice here is all of these 3 are enclosed, but you needed the center pin to come out. That means the length of the core and the outer has to be little small, right? And I'm making all these small things so that you can understand if you made a mistake, how can you go back and correct it, right? So the height of this core has to be slightly less. For example, here I would like to keep it 3.5. In a way, now it will give you like 0.5 mm of the center conductor lead. But depending upon how much lead you need, either you can reduce it or you can increase the center pin height. And similarly for the core or the outer shell, I'm going to do it 3.5, and now you will have the proper looking object which a lead protruding out. Now finally, what I need the mounting flange, and although that flange is not necessary, it's not mandatory, but just to give it a realistic feel. So let me first orient it in the X looking direction, and now we can use this 2D to 3D transformation just to show you variety. So we go to extrude. You can see the drawing plane is XY by default, so I'm going to change it to YZ first. Right, and then here you can see the origin is here. I don't want to draw. I would like to draw on this face because that's where I want to create a flange. So I can shift the X origin to 3.5. Right, so this way now I'd be drawing onto this. So this is basic 3D drawing fundamentals, which I assume you already know if you have used a lot of other 3D tools. Now here I can use this rectangle, and then depending upon how big flange or how small flange you want to draw, you can draw the flange, and then finally go to the extrude tab, and here you can either extrude it in this direction, which is actually the reverse of what we want to do because your center pin is here, but you can pull it back. So here in extrude distance I can give it -1, or I could have given origin which is less than 1 compared to this coordinate. So now you have the right flange at the right place. It's 1 mm thickness. That's okay. And now you have the connector. Now all of them looks like the same color because everything by default is unknown material. Now our idea is about adding material, and as we already discussed, we can get the materials. So right click, you can select it from the library, and here these are the library which you can again pick. But here in EM Pro, what you can also do, you can create your own library. So in case you have created your own kind of library or EM Pro library, you also will have access to those, and you can add it. But right now I have not created library with my favorite materials, so that every time you need a material, you don't need to go through this long list. You can have your own favorite materials. So here let's go ahead and add gold I would need, and then PTFE. So while highlighting this, let's go ahead and find PTFE, press the shift key. That way I could add both of them together. So here let's first rename this model to flange so that you can identify the proper objects. Now before I go to assign material to these objects, let's create some Boolean operation, because right now everything is crossing each other. So it will be a good idea to properly Boolean. So here first of all I would like flange and I would like to take out this outer shell from the flange. So select flange, press the shift key or the control key and select outer, right click, boolean, and you can do subtraction. So what I would like to subtract outer from flange, but I don't want to delete outer, so let's keep the original outer. Click OK, and then the boolean operation has happened. You can see the icon change. Then selecting outer, I'm going to select core because that's what needs to be subtracted. So let's go ahead and subtract the core from outer, and I would like to keep the original of the core, only the outer should be the resultant difference. In here you can see that operation. And finally, from core to inner pin, right click, boolean, subtract, and I would like to keep the inner pin original. Click OK, and everything is done. So now, before we assign the material, if you want to see whether really everything has happened properly or not, you can switch off all the parts viewability. Now here, click on flange. You can see the object with the boolean operation. Outer, you can see the hollow conductor, and then you have a core again with a hollow inner pin, and inner pin is our solid, kind of cylinder. So everything's pretty good. Now click on this parts again, everything is visible. Now to assign parts, simply take this gold, assign to flange, so it's all gold plated conductor I'm going to use, and then assign the core as PTFE and gold to inner pin. Alright, so now you have a pretty decent looking SMA connector, and if you want more attributes, you want to chamfer the edges or blend the edges, you can do so, but essentially that do not affect any of your RF performance. Now once you have the design, let's assign a waveguide port quickly like we did. Right click, new waveguide port, select the phase, which is going to be this coax phase. Boundary extension, do not want to extend, just limit it to this phase. 50 ohm voltage source, impedance. Click on this plus icon, select the center of the inner pin here, and then finally another on the shell. So now you have that impedance calibration line, as you can see. Click apply, and in order to simulate, you can either click on simulate directly and it will ask you to save. I'm going to save this also in the same demo video library, and here let's name it my SMA. Click save. Now the geometry has been saved, and now it is running the analysis on the geometry to make sure indeed we came up with a 50 ohm coax phase or a 50 ohm connector. So again, few seconds and it's done. Let's look at the result. Impedance PI, right click, double click, and you can see it's a nice 50 ohm calculation or 50 ohm impedance offered at very high frequency. So now you have seen both the varieties. Number one, if you have a vendor 3D CAD model, how can you import it in EM Pro, work with it, assign the material, save it into library, as well as you have created your own SMA connector and you have saved it into the library. Now let's understand how do we use all this into ADS. To use EM Pro components in ADS is rather pretty straightforward. So while we are here, let's open ADS, and now let's create a new workspace. Give it a name. For example, here let me give it a name, Demo 3D Component Part 1, as our video title is Part 1, and I will set up a layout technology immediately so that I have the right layers stack up for the placement of these 3D connector models. Now once we go ahead and create a workspace, we can create our own PCB technology or use the standard technology layers which are available. For this demo, I'm going to create my own PCB technology. I will select millimeter as my unit, number of layers as 4. Click on next, and here you can see I have 20 mil, which is 0.508 mm for the dielectric, and all these properties of dielectrics you can change later after your workspace is created. Now once done, here is your workspace, and we do have a technology which is 4 layer, and again if you need to change any properties, we can easily do so. Now once we have the stack up, I would like to place connector which we just designed in EM Pro on top of this con layer, and for the transmission line made in con layer, I would like to use M2 as my ground reference. Now the question is, how do we calculate 50 ohm impedance? Of course, you can use your theoretical formulas to calculate. However, in multi-layer stack up, sometimes you are going to design lines on in between layers, and sometimes you are doing it on top layer. So here in ADS, you have a built-in control impedance line designer utility, whereby you can synthesize and calculate line properties for microstrip, strip line, as well as CPW. In my case, it's a simple microstrip, as you can see from the snapshot. It's on the con layer, and M2 is declared as the ground by assigning the properties here. Now with this stack up, I can go ahead and start with 1 mm, for example, analyze the line and see what's the impedance offered. So it's already pretty close to 50 ohm. However, it's not exactly 50 ohm. So if we need to optimize it, we can go to optimize mode, and then we can optimize the width of that line in order to achieve 50 ohm on that stack up. Now here we can see it's around 0.9 mm, which gives me the right impedance I'm looking for. Let's go ahead and close the CILD. We got the information we were looking for. Alright, so now how do we get EM Pro models into any ADS workspace? It's pretty simple. Go to Design Kit, Manage Library, and here we can add the library which we have just worked upon or created. Now here on desktop, I do have a demo video lib, and that is what I'm going to point to, and the mode will be shared so that you can see all the components in that library inside ADS workspace. And here you can see I have two components which are populated. One is the imported signal microwave connector, and another with the SMA connector which we just created. Now if you go to library view, you can see two libraries. One of course is the ADS library, which only has the stack up at the moment, and then we have demo video library, which contains the EM Pro component. Now each of those EM Pro components, you can see you have variety of views. EM model currently will be blank because we have not performed any active simulation in EM Pro. But if you have performed an FEM kind of analysis within EM Pro, then you will have the results available, and that result you can directly use in any ADS circuit simulation by placing the symbol or lookalike symbol onto your schematic design, connect it with the rest of your circuit, and you can directly perform simulation. The data will be reused from the EM Pro analysis. If you have the database empty, then you can perform an EM analysis on that 3D component. Now another two views which are exactly the same, the footprint and layout, and these are the views which basically gives you the symbol which you can place inside any top level layout, wherever you are placing these components. The EM Pro view here is a 3D view, and here if you need to make any modifications to your 3D object or change any material parameters, you can open that design into EM Pro. For example, if I try to open this, first time when you do it, it will ask you to select the EM Pro home directory. Where exactly is your EM Pro executable? Now you can point it to the EM Pro executable available inside your ADS installation directory, or if you have installed EM Pro as a standalone software, you can point it to there. So in my case, I will go to C, Program Files, Keysight, and that is where I have my ADS installation. Browsing to that folder, going to FEM folder, and then simply following the path. And Win3264 is the folder I'm looking at. Inside it, there's a bin folder of EM Pro. So once ADS knows that path, it will create a configuration file in your home directory, and then it will automatically open EM Pro next time whenever you are doing this exercise. So here you can see the part is open in EM Pro, and you can make any modification, do the save, and as soon as you save or make any modification, it will be live updated here. Right, so pretty simple, fundamental. Now let's go ahead, go to library view, because since now we have multiple libraries, it makes it easier to work in the library view instead of folder. Now first thing I would like to do, and I recommend everyone to do, since you are going to use EM Pro 3D component, it's a good idea to let ADS know the layers on which you may have the 3D connector in order to connect any termination of ports, etc. So to do so, we can close all the designs so that nothing is open in ADS, and now simply you can go to options, technology setup, and here you can see I'm in the ADS library, and in reference library I can add a reference library which is EMPRO standard layers. By having this library, now you have all the definitions of pins, etc. whenever you use EMPRO component inside ADS. It's a pretty simple thing. Again, one time you need to do it, and now you have all the layers available. Now with that done, we can right click and create a new layout in our ADS library. You can name whatever you want, and in this library, remember we already calculated the 50 ohm line, so we are going to make the 50 ohm line here and place the connector. So how do I place this connector model into an ADS layout? Simply drag and drop the layout or the footprint view, and you can place it into the ADS layout. Rest of the operation I will show you later. So right now I'm simply placing it into the layout. Now for transmission line, we can go to parts, or you can use a rectangle and draw the rectangle of the desired size in terms of width and length. But here I'm simply going to use the microstrip line. The width we just calculated is 0.9 mm for 50 ohm. And I'm going to give something like 12.5 mm, which is like ½ inch. And I do have a transmission line which is placed here. Now we can simply align these two components. You can see the lead is facing leftwards. So I can simply select this 3D component, press Ctrl R to rotate. And now you can drag and place this component wherever you want. And again, if you have a problem aligning it properly, you can simply switch off the grid snap, and now you should be able to pick up the component and align it exactly to the point where you are looking to place this 3D component. And here you can see also the outline of the ground lug of your SMA connector, and this line clearly can be seen not shorting with that ground lug. Pretty simple, straightforward, right? Okay, along with this, you can also see two of these blue icons. They represent the terminals of the waveguide port, which you kept in the EMPRO while creating the component. However, we don't need to connect any pin here because we will directly use those pins inside RF Pro to create our termination. Now, once you are done, very simply, let's place a pin on this end of the transmission line. Otherwise, you can drag and drop another connector, and you can connect the SMA connector even on that end of the line. But here, right now in my demonstration, I'm only going to show one connector. Alright, so now how the connector body will connect to the ground, which is on M2 layer. Remember, we synthesized a line where we had M2 connector or M2 layer to be used as a reference or ground return. So here I will enable the grid again. And now by going to layer menu, and in case this layer window is not available, simply right click anywhere in the toolbar and enable the layers window. Here we can select M2, and that becomes our active drawing layer. Simply draw a rectangle which is basically going to create a kind of ground conductor at the bottom layer. And again, now we need to provide a connection going from the top layer to connecting to the con2 or M2 layer. And here again in the con layer, we can simply draw a couple of rectangles here just to provide that kind of via hole, or use it as a via hole kind of reference. So here, by creating those two rectangles on either side of the transmission line will allow you to create the kind of rectangle or the ground pattern on the top con layer you are looking for. Now, how does the con and M2 layer gets connected? If you look at the stack up, the through via here is con2. That's the layer in which you have a through via. In case you had a blind via going from con to M2, you could have used that, but as per our stack up, there is no via layer which is mapped, so not a problem. So here, let's make con2 as our active layer. Simply select on circle, and now you can draw some via circle here. And for example, once you draw one circle, you can select and again go to properties, and you can change the radius the way you want. And here in this particular case 0.2 mm is what I want. Simply Control C, Control V, and let's place some vias. Now when you're trying to design an optimal transition, of course you will do the proper placement of the vias, but here I'm just showing you the basic concept of using 3D component in ADS. So I haven't put enough attention on how much should be the separation, how much should be the via to via separation, and so on. Okay, so now everything is set. So now what we can do is launch RF Pro, and we can see this geometry into 3D because now we already have the connector, the transmission line, the ground connection. So before we go to RF Pro, we can also check the connectivity, because we don't want to be in situation where we placed everything and then we run analysis if something was either open circuit or short circuit, which can happen on some of these alignments. So before we go to RF Pro, we can actually open this design in 3D preview by clicking on this icon, and using that option we can check all the desired connectivity of our assembly. So here you can see nice assembly of SMA 3D connector, and then also the transmission line and the ground layer. Again, one interesting thing you notice, the center lead of this connector is basically going below the transmission line. And now why that is happening, if you recall when I was importing this model and we were talking about origin point, the Z origin was right at the center of this inner pin. And when you place this component in ADS, it kind of aligns with the same Z origin, and that is why you are seeing it. But it's not a big problem to figure out. We just simply need to shift this connector a little upwards by the amount of this radius, or slightly less than this radius, and then it will align properly. For simulation purpose, that's still not a problem. You can go ahead and simulate it as it is and it will still work. Now before we do that, let's quickly check the connectivity and make sure everything is, the ground lug is connected to ground layer, all the vias are connected properly. For that I simply turn the conductor to wire frame, and now using this ohm meter or kind of connectivity engine, if you select and if you click on the body of this SMA, you can see the SMA lights up, and also the bottom plane, which is M2 layer, lights up. So that means they are connected. Now how about the central piece? So we open it up, click on ohm meter again, and this time I will connect on this transmission line, and here you can see the center pin gets highlighted, so that means the entire signal path is connected. So this gives us basic confidence that everything is working okay. Alright, so now how do we correct that alignment problem? If we double click on this 3D component, and here you can see you have a parameter component offset Z, and here I'm going to simply offset it by 0.05 mm, which is roughly around the kind of radius you have, and it will just push up the 3D connector. So with that, I don't need to go back to the 3D mode, but in case if you want, you can go to 3D view and check the connectivity again. So at this moment, let's launch RF Pro and make sure we have the right assembly which is ready for our EM simulation. Here indeed you can see you have the right assembly, pretty much what was shown to you, and here the lead is a lot upper than what it was earlier, right? We still have slight part below this transmission line, but you can provide a little more offset and everything will be proper. For this study, let's stick to this. Now here, in order to set up analysis, we just need to create a port, set up our frequency sweep, and go ahead and run the analysis. So how do we go about it? Well, your 3D connector, as you can see, it is coming up in the component model. If we expand, you have the instance name of that connector, and inside you have those waveguide port pins. So we can simply select both of them, drag and drop, and connect the port. And here you can see we created plus and minus termination. And what about other pin? Because we also have a pin which we placed on this transmission line. Now for that, we have to use M2 as our reference layer or ground layer. And that can be simply done by adding M2 as a reference pin, so that RF Pro knows that that's the layer you need to use to place a negative pin. So simply right click here, create a reference pin, select M2 as one of the options. Now if you drag and drop this P1 pin onto port, it automatically places the minus pin onto that M2 layer. As you can see, it's pretty straightforward. Now, final thing remaining is to set up the port calibration for both of these ports, because I would like to use waveguide port, especially on the coax connector side, as well as on the transmission line, because it's like an end of our structure. So we can easily use waveguide port, or some of you, as you call it, wave port in some other tools. So to do that, simply right click on the port, go to properties, and here in feed type, let's define TML. So TML will create a waveguide port wherever possible, and especially both of these ports are on the periphery of our structure, so obviously it will create the waveguide port. After that, we can go to options, set our frequency sweep, go to simulator, make sure it is FEM, and we are ready to go ahead and simulate. So let's go ahead and run analysis. Now, while that analysis is running, if we look at other topics we had, I promised to show you some of the different type of assemblies and analysis. So while the simulation is running, let's go and look at some of those options. So here I do have a ADS workspace where I have imported the signal microwave library, and again, like previously shown, it is using L40, and I have also used the top launch or the top side connector, which is again up to 40 gigahertz. So both of these are assembled into a library exactly like how we work, and these connectors are now used in our design. So here under SMA connector launch, I do have almost the same assembly which I just showed you. It is using the L40 connected to a transmission line like we just did. Now for this, simulation has already been performed, and if you open the results of simulation and look at S parameter, and here we can go ahead and look at XY graph, plot S11, and here you can see excellent return loss right up to 40 gigahertz. So that tells you it's kind of pretty good in transition which I ended up creating. And here's the transmission response, which also looks pretty nice and linear, linearly changing with frequency. So if you do your transition design properly, you should see a pretty good frequency response. If you don't, you can optimize it a little bit, and we will talk about all those things in the next video. So that's one of the example. The second example is again using a topside connector, and again this is using TLF40 model from Signal Microwave website. And again, it's nothing different. It has been used exactly the same way. And here you can see the topside connector touching the transmission line. And you have a transmission line, and this one I created something like a CPW with a via array and a lot of vias around the transition of where this is happening from coax to microstrip. And again, we are going to talk about some of this in our next video. Now for this assembly, again, if you look at the response in terms of S parameter, and again you can see pretty good return loss all up to 40 gigahertz, and also the transmission response looks fantastic till 40 gigahertz. So once you know the fundamentals, you can get creative. If I had my own filter, power divider, amplifier, any kind of circuit which I'm simulating along with 3D connector, and I would like to see the full composite response, this now you have the power and the capability to do so because your fundamentals are all clear. All right, finally, I'll show you one last, pretty complex assembly where you can utilize the power of both RF Pro as well as the flexibility which is given to you by modeling your own component in EM Pro. So here we do have almost 40 plus SMA connector, which you will see just now. It's one of the Keysight reference test boards which we use along with our instruments. In here you can see the 6-layer board with plenty of SMA connectors at the top, and then you have plenty of SMA connectors at the bottom. So this entire assembly is done in ADS layout, and we have opened it in RF Pro. Now when you have to analyze this kind of board, you obviously don't want to simulate the whole board as it is, but you can see there are plenty of traces and plenty of interconnects which you would like to simulate. And RF Pro has a nice capability of doing user-defined EM extraction, whereby you can pick and choose what analysis or what section of the board which you would like to analyze. And you can do so even with these 3D connector models. So let me set everything to wireframe so that you can see what exactly I'm trying to show here. And again, if you want, I can switch off all the components or switch on, but right now this does not have any schematic component. It is all transmission line. And here in one of the example, I have this BAT line, and here you can see I'm simulating only one specific net, which is now getting highlighted. If you see this green trace, that's the one I'm simulating. It's a strip line. And then you have this SMA connector to strip line transition on either ends, which is included in our analysis. And the SMA connectors which are used are added into this analysis using parts. So here you can see I have two SMA connector, one on either side of that net, which is included. And now if you look at the response in terms of S parameter, you can see the composite response of that analysis. And again, this is BAT standard, so it is not supposed to work like a linearly decreasing fashion. These resonances are pretty much intentional in this structure, what you're seeing. So again, the idea which I wanted to give here is, even if your assembly is so complex, you can easily do all that in ADS layout and then use RF Pro to analyze such structures with great ease. Alright, so now let's go back to our analysis, and you can see it's complete. It took like 2 minutes on my laptop. And now once we look at this parameter of the assembly which we just did in this video, and here you can see non-optimal performance beyond 7 gigahertz. And again, as I said, I'm not doing a very optimal launch design, but these kind of effects you can see even in your actual board. So you need to be very careful, and you can see you have caused an undesired resonance, which is not extreme, is only 1.6 dB, but again, it doesn't look pretty good. It looks actually ugly. So you need to put enough attention on how you are connecting your SMA connector with your RF board, and you have to be careful when you're designing. And that's exactly leads to our part 2 of this video on how to optimize SMA to microstrip or SMA to strip line transitions, so that you can have the best possible performance of your RF circuit. That includes the 3D component transitions as well. So that's all for this video. I hope you like the content presented, and it will be useful for you to get started by including some of these 3D components in your design. It has been a little long video, but I truly appreciate you sticking till the end of this video, and I hope every minute you spend on this video was worth your time. So wish you all the best in your design work, and look forward to see you in part 2 of this video series. Thanks again, and wish you all the best.